Hello everyone, welcome to the final lecture of week 5. So in this week we have been discussing about transformer architecture, and in this lecture we will focus on various interesting aspects of transformer, especially how do you bring in efficiency at different levels. So that's why this particular topic is named as efficient transformers, and we will touch upon various different aspects like how do you bring in efficiency in decoding through KV cache, how do you use transformers for long sequences. So various attention patterns that we will talk about. So we will talk about grouped query attention and also briefly sparse mixture of experts architecture. So let's talk about KV cache. This is one of the very buzzwords when you are using transformers and decoding. So what actually we do there? So when we are doing training, so let's look at the decoder. So we can compute attention in parallel, right? So, but what happens at inference? Inference times you are doing autoregressive prediction. So you are predicting one token at a time. So you give a start token and you will only predict one token. So you have no idea about what is going to be in the future sequences. So you will now again start from I and predict the next token, right? So you do one by one. Now because you are doing that, so every time you have to compute key value and query for everything, right? All the things that you have seen, and you may have to do repetitions in that computation. Okay, so we generate one token at a time. So for any new token that you're generating, I need to multiply by all the matrices, query, key, and value matrices. But you have to recompute the key and value matrices every time by default, right? So if you want to avoid for all the previous words, so you have done it for start. Now when you are doing it for I, again you have to recompute for start as well as I. I want to avoid that. So how do I avoid that? Idea is very simple, caching. That whatever tokens have already been processed, their key values have been computed, you just store them. You don't need their queries because you will query only through the new word, right? But you will need the key and value from the previous tokens. So you just cache them. That's the idea of KV caching. So you can cache them so that you can just grab them from the cache and need not recompute them every time. So this is what we typically do. So suppose we have a sequence of n tokens, and dk is my dimension for the query, key, and value. So I multiply n cross dk, dk cross n, and I got this n cross n square self-attention matrix. And then I multiply it with the values n cross dv, so I get a dv dimension, n cross dv dimension output, attention outputs for all the n tokens, right? So there were 4 tokens, I got attention output for all the 4 tokens. Now, what is query caching telling us? That okay, so in decoding time you will only do one word at a time. So at the inference time in decoding, so when you are doing for Q4, you don't need these queries, and all the previous keys would already have been computed. So you just cache them, you don't compute them again. So I am doing inference at the decoder. So I have a new query and I need to multiply it with all the keys. So these K1 to K3 are already in cache. So they are already in KV cache. I just compute K4 and I get, so I retrieve K1, K2, K3 from the cache, compute K4 and I get this matrix, these values. And similarly for the values, I have them in cache. I just project to V4 and then I multiply this with this and I get the attention output for the 4th word. So this is what is KV caching, so that you cache the previously computed key and values and just retrieve them. You do not have to compute it by using the word embeddings for these words again and again. And this brings in a lot of efficiency at the decoding time because, right, you are only computing for the new word that has come. Everything else is just a lookup. Right? Okay. So now in general, transformer language models are quite slow. So this is just a simple estimate of time, one page on a particular GPU. So suppose you are generating 100 tokens, and your previous context, the prefix is already 100 tokens, so you take that much time. If your prefix increases, your time increases, right, linearly, right. So it's a linear increase. Yeah. But what happens if you generate 100 to 200 tokens? So you see the time increase, right. So this is just n square of the tokens that you are generating, right. So this will be if this is k, say c is the context and n is what you are generating, it will be n times n plus c typically, right. So that will be how the computation will happen. So order n plus c. So because you are getting keys and values from everything and multiplying them, right. So that's why 2.3 to 4.4, 4.4 to 7.3, right, it increases. And here there is a linear sort of increase. So 1.1 and roughly same. Right. So why does that happen? Because we have seen the main computation that happens in transformer is this scale dot product attention, and where I am multiplying. So if I have an n sequence length, or n is my sequence length, I am multiplying queries. So each of the word will give me a query, and this each query will be multiplied to all the n keys, right. So one query gets multiplied to all the keys, and that's what I do for all the queries separately, right. And that's where I get this matrix, n square matrix, right. So that's what we saw in KV cache. So you have this n square matrix that we get, and that is what is the computational and space complexity and time complexity of transformers. I need this n square memory, and that's what prevents us from using transformer for very long sequences, because it is always increasing by n square. So there have been a lot of effort in reducing this computational complexity of transformer from n square to linear in n. Right? So we will see some of those efforts, that what are the tricks that people have used. So one of the very basic ideas that, okay, so I have a global attention here, right. I mean, even if I am doing decoder, I am attending to all the previous tokens that have been generated. So one way could be I can just do very sparse attention. Let's say at particular token, wherever I am, I only attend to at most previous k tokens, right. So suppose I am here, so I'll say I'll attend to previous 3 tokens. I am here, only 3 tokens. So like this is a scenario in decoder, and encoder you may do it symmetrically. So k tokens before, k tokens after, right. So this is one way of doing attention, I mean limiting your attention. So then you can see the computation will be simply k times n for an n sequence length, and it will be linear in n. So if you reduce your k, or if that is constant. Of course, there are various variations people have tried, that you can attend to tokens in a block. So you can define some blocks, and in a block a token will attend to tokens will attend to each other. Right? That's very similar. You can do sliding window based attention. Right? This is very similar, like what I am showing here, but the sliding window can be also for encoder, and so on. So we will see some more examples of these local attentions. So there is another kind of architecture like a sparse transformer, where the idea was that you can use multiple different heads to do different kind of attention. So like suppose you have 12 heads, so you can say my half of the heads, the 6 heads will do one kind of attention, another 6 heads will do another kind of attention. So that way a single token can attend to multiple different type of tokens. Like here what they did, half of the tokens are doing local attention. So this is in a block, so that is if they are in the same block, so you have defined some blocks here. So this is, if you are in the same block, you attend to each other, right. And this is decoder based attention. So you attend to all the tokens previously in that block, and then the remaining heads will do strided patterns. So you are attending to some fixed patterns, right. So this is, and their different heads are doing different patterns, so that overall you are having attention over more tokens, right, in different kind of attention. And this idea has been there for multiple different kind of models, like Linformer also proposed multiple different kind of attention. Like in Linformer, what they said, so this is what is your full, so this is now again back to encoder setup. So you have full n square attention, each token can attend to each other. Now you can talk about sliding window based attention, right? So what is that? So you take each token will go to say previous, say 3 words and next 3 words, right? So you can have fixed window. So so this window is like window of size 7, right? So window of size 7, and if what will happen, so you are as such only attending to 3 tokens before, 3 tokens after. But if you look at transformer with L layers, this would actually increase the receptive field. How? So you see at the layer 1, a token is attending to only W previous tokens, right? But now you can see in the second layer, this token can attend to these 3 tokens, and these tokens are anyway attending to these tokens previously. So your receptive field is increasing, and so on. So if you go to Lth layer, so your receptive field is effectively L cross W. So this token could actually attend to all the, L cross W tokens going over L layers. Okay, so the receptive field size, the effective size becomes L cross W, and that may span a lot of tokens in general. So that is the idea. So and then you can even increase the receptive field if you use dilation like you do in convolution. So that is, you put some gaps in this. So here, so for the same window you have now L cross W cross D. So what you can do, you can increase your receptive field by dilating the sliding window. So you had this, suppose you are using dilation D. So you have, so effectively for each layer you have D cross W as your attention span, and the overall receptive field for L layers will become L times L cross W. So this is here dilation is 1. So you are having a gap of 1 in between, right? So your effective span increases, the receptive field increases. So these are the kind of patterns that Linformer used, and they also said that okay, what I can do, so I can use the idea that different heads can use different dilation configuration. So it may happen that some head is not using dilation at all. So I'm focusing locally at completely, while some other heads are doing dilation 1, dilation 2. So you see, we are playing with 2 things. One is the heads. So different heads can do different kind of attention. So some heads are doing dilation 0, dilation 1, etc. And then the second thing, we are playing with the layers. So the layers are increasing my receptive field, right? So here is where how I am increasing my receptive field, and heads are trying to do variation. So you can do variation in your attention. So this is how they are able to actually cater to many different tokens, attending to many different tokens by using the heads and the layers. Okay, so overall, finally, what was the attention that they used was given in the picture D. So they again combined something called a global attention with this sliding window attention. So what was the global attention? So they would pre-select some tokens input location, and they will have a symmetric attention. That means all tokens are attending to these, and they are attending to all the tokens, right? And what will be this global tokens will depend on the problem. So let's say you are doing classification. So the CLS token is very crucial. So what they will do, so CLS token will have a global attention. So you will, every token will attend to this, and this will attend to all the tokens, so that you can do classification on top of CLS token. Similarly, if you are doing question answering, so question is very crucial. So all the words of the question would have a global attention. So like that, they defined for various tasks, different tokens would get global attention, and that's how they were able to combine global, sliding window, and so on attention, and they got a huge, they were able to cater to very long sequences, 4,000, 16,000. Another very similar approach came as Big Bird, where also they tried to use multiple different kind of attention, right? So they combined random attention, window attention. So this is very similar. So they didn't talk about dilation as such, but they will have a sliding window, global attention, very similar to Linformer, and they combine all that. So then what will happen? Each token will attend to some global tokens, some random tokens, and the window based attention. So some words before, some words after. So it has, I mean, different kind of attention spans. So like here you can have 2 tokens that you are attending randomly, a window of size 3, and a global attention with 2 tokens. And this is how the combined model looked like. And even the global tokens are defined in 2 different ways. So one was that, okay, you can take some actual tokens in the input and make them global. So let's say I'll take, say, 2 tokens in my input and call them the global tokens and attend to that. Or you can have some external tokens. So you can create some external tokens like CLS token. So this was what they call it, ITC versus ETC. So extended transformer construction. So here the effective input length is increasing. So you already have some input W1 to Wn, plus you are incorporating some extra global tokens, say Ng. So then you're doing n plus Ng times n plus Ng attention matrix. Whereas here the matrix size will remain n, where n is your input, right? So here your matrix size increases, here it doesn't. The good thing about this part is that even though you are increasing your matrix size, you are incorporating some global tokens, I mean some external global tokens, right? So they may have their own significance, whereas here you will not know which part of input you really want to put global attention. Right? So okay. Now coming to another kind of architecture, Linformer. So where they try to do a low rank approximation for doing the same task. So whatever we are seeing till now, Longformer, Big Bird. So the idea was that they were able to take from order n square computation to order n times some k, and k is much smaller than n, right? So they are able to use a window and so on and so forth, right? So that is the idea. They are reducing this particular complexity from n square to nk. Now Linformer also does that in a slightly different manner. So what is the idea? They use some low rank approximation of the n cross n attention matrix. So by projecting this n cross d key and value to n cross k, right? So we will just see quickly how that happens, but this is the motivation. So this is your transformer model. So as you increase your sequence length, right, from 512 to 65,000, so it's increasing, the inference time is increasing, right? And this is not a linear scale, so it's a square, I mean increasing as a square. But on the other hand, for all the Linformer variants for particular k, you see this remains constant with sequence length. I mean does not scale increase so much. It is increasing but not so much, right? It is increasing in the transformer architecture. So what was the idea? So to get an intuition what exactly they are doing, so let's see, suppose we are having n tokens. So n is our token, n is our sequence length, number of tokens, and dm is our embedding dimension, and let's say dk is our key or value dimension. Both are dk, right? So originally what do we do in the normal case? So each so we take the embedding and project it to using this model dimension times key dimension, right? So we start from n cross dm, and this is your embedding, and you multiply with dm cross dk matrix, q wq wk and wv, so that you get an n cross dk matrix, right? And these n cross dk matrix are obtained for all query, key and value. You have an n cross dk matrix. So you have n cross dk for query, and for key also you have the same. So you take a transpose, you get dk cross n for key. So together you get n cross n, this whole attention matrix, right, from query and key, and then you multiply by v, that has n cross dk again for v. So n cross n, n cross dk, you get n cross dk, right? So for all the n words you get dk dimension attention output, right? So dv dimension you can say. So that's what you get an n cross dk dimension output. I still want to get the same output. I still want to get for the all n words, I want a dk dimension or dv dimension output, right? But I want to save in this computation. I don't want to compute this n cross n matrix, right? So what is the trick that they are using? So they are having this additional low dimension projection, this k cross n matrix, that they multiply for both key and value, not for query. So only for k and v they will multiply this, right. So what will be the impact of this? So for both k and query, not the query, the key and value, I'll multiply by this matrix, and that's why I get the k cross dk matrix. So what will happen now because of this? So I'll have, so let's see. So what will happen? So think about this. This is from their paper. So they use this q, k, and v, but this is just the embedding matrix, which is, an embedding is n cross dm, model dimension, right? And this is your dm cross dk. So originally, what you will do is you don't have this ei and fi, right? So you have n cross dm times dm cross dk, so n cross dk, and then you have, this is dk cross n, this gets you n cross n, and this is also n cross dk dm cross dk, so n cross dk, right. So effectively you get n cross dk. But now what is it that they are doing? They are having this matrix ei, and ei is a k cross n matrix, right. So k is very, very small compared to n. So what will happen if you multiply ei with this? So ei k wi, right. So ei is k cross n matrix, and you have key is just the embedding matrix, so n cross dm, and wi is dm cross dk. So you multiply these, so you get k cross dk, right. So k cross dk, same here. So you get a k cross dk to the transpose, so dk cross k, right. So now you will have n cross dk, dk cross k. So effectively you get n cross k, right. So this is your new matrix. So rather than getting n cross n matrix, your p bar is n cross k, right. So that's why you are saving not n square but n cross k, right. But remember, we finally want n cross dk output. So how do they achieve that? So even in the value matrix, they multiply with another projection fi. So fi is also k cross n. So you will again have k cross n, n cross dm, dm cross dk. So this will give you k cross dk. So you have n cross k is your attention matrix, right, and then you have k cross dm, and this gives you n cross dm, right. It should be dk, k cross dk, so you get your n cross dk output. So you are still able to get the output, but your effective computation reduces to n cross k rather than n square. So that's so they are achieving it by having two extra projection matrix ei and fi, right. And this k they said was much smaller than n, as you can see also in this picture. This k is like 128 and so on, and effective sequence length can go up to 65,000 and so on. So they use a very small value of k for projection. Okay. Now coming to another aspect on how you can save in computation. Right? So till now we talked about various attention patterns, but here another way you can do is by saying that, so in general this is how your multi-head attention goes. So you have, let's say you have h heads. So you have h copies of query, key, and value matrices, right. So projection matrices. So first of all, in the same year, multi-query attention was proposed. So this was in 2017 or so. So where the idea was, okay, what if all the heads share the same key and the same value, but you can vary queries across the heads. So you can vary queries, but the key and value will remain the same, right. So this was the multi-query attention. You share a single query and value heads across all the query heads, right. So this was there, and recently the grouped query attention was proposed, where they said, okay, now this becomes, too much, because you may have many heads, and you are saying I will just use one particular value and key for all the heads. So what you can do, you can group. So you can say, okay, I'll use a group of heads. So let's say for 2 of the heads, I'll share key and value. For another 2 heads, I'll share the key and value. So this is like a grouped query attention. So you're grouping certain heads, and for that heads, you are having different queries, but the same key and value. Right? So this is the grouped query attention from here. So this is like an interpolation between multi-head and multi-query. So if you group for all the heads, you get multi-query. If you group for single head, you get a multi-head attention. Right? And you can see that the computation reduces because of, and the storage also reduces because of this, right? And they found some nice, they did some nice experiments saying that, okay, so this is your multi-head attention. So this is a large model and double XL model for T5. And what they found, that if you use multi-head attention, this is the time per sample for large model, which is small. If you use a double XL model, your time increases a lot, right? But your performance also increases. Now, if you do, instead of multi-head attention, multi-query attention, so even double XL you can do with less time. You see that your efficiency is increasing. So even a double XL model you can run in less time than the large model, right? But your performance is dropping from double XL model, right? So you lose on performance, right? You are getting better than large model. So I mean, if you want to save time, this is one of the good ways. I mean, you have taking less time and better performance than large model, but you are losing compared to double XL model. So they said GQA is a nice spot where it takes slightly more time than this, right? But it's still less than the large model, and performance is much higher than this and comparable to the double XL model. So this GQA is a very sweet trade-off between time and performance, and that's why this has become quite popular. Of course, this was T5 large models, and T5 large models use multi-head attention. So how do you modify that architecture so that can start using multi-query and group query attention is something interesting. So we use something called uptraining, and this we will learn when we talk about pre-training in the next week, right? So we will talk about what is uptraining and how do you start from a T5 model that has already been pre-trained to use something called something like multi-query attention, multi-head attention, right? So we will talk about that in the next week, the last lecture of the next week. Now, another kind of architecture that has become very, very popular and important is the mixture of experts architecture. We also call it MOE architecture. So what it does is very, very simple as such. So the only place where you make change is your feed-forward network. So this is your normal architecture for transformer. You have self-attention at a normalized feed-forward layer, and again at a normalized. So what it does, it divides the feed-forward layer into multiple blocks. Each of the block it calls as an expert. So let's say I have in the feed-forward layer, I have certain parameters. I divide into 4 blocks, right, of equal sizes, and I call them 4 different experts. Now, whenever I get a token, right, so I am getting tokens one after another. So whenever I have a token, so this is happening independently. So each token, after you have got the self-attention output, the normalization, I pass it through a router, right? And this router does very simple thing. It just computes probability for all the experts. So it computes distribution over the experts. So which expert should I route it to? And suppose I find that the second expert has the highest probability, so I can just route it to that. Of course, the formulation in general, you compute probability and you can actually route it to all the experts with their probabilities, right? So that's the general formulation. But when you do sparse mixture of experts, you just route it to one expert among these, right? So similarly here, suppose this is probability 0.8 to this particular expert, so you just route it to that, right? And then again you continue, right? So what happens in MOE? So it operates independently for each token in the sequence, and the router can route each token independently to one of the experts, right? Now, if you want to look into the equations, how this happens is also not very difficult. So let's say, so you have this router variable WR, and this is your input. So input will be simply the model dimension, right? So x will be of dimension, model dimension, and WR will take the model dimension to the number of experts. So WR will be you can say number of experts times dm, right, if this is dm cross 1. So I mean you can play with the dimensions. So the idea is that WR when multiplied to x will give you n dimension vector when n is the number of experts, right. So this is the logits that you get. So each experts, you get a value for each expert when you multiply the input with this WR matrix that is trainable. Now once you have the logits, you simply do softmax to compute the probability, and then you can say okay, I'll use the probability, and accordingly I will pass it through each, I'll get the output from each of the expert, and this will be my final output, right. And if I using a sparse model, you can simply use k equal to 1. So that is, I will I'll take just the top expert having the highest probability, I'll route it through that, and this will be as if you're simply passing through this a smaller feed-forward network rather than passing this large feed-forward network, right. You're doing computation here, and you're doing the further layers, going through further layers, right. So that is your sparse mixture of experts that also has been shown to be more efficient, because you can use more parameters, but then they can be divided into experts in the feed-forward layer, so that the computation actually goes through only a smaller portion. Okay, and what do these learn? Typically, they are learning at the token level. So different experts actually handle different tokens. Like it may happen that the one expert is in each layer. So you have these experts in each layer. So in layer 1, expert 1 is handling punctuation, expert 2 is handling verbs, conjunction, visual description, right. Especially that happen important when you are doing some mathematical operations and all. So it may happen that you have a number, and then you say okay, I have an expert for numbers, so this will be only passed through that particular expert, right, routed to that, and it computes the final output, right, while normal verbs etc. will be routed through different experts, right. So this is the MOE architecture in very short, and this particular blog actually gives you more details if you want to look into that. Okay, so this completes our week 5. So for this particular lecture, you can look into the chapter 10 of our SLP3 book, but many of the things I talked about are from research papers who I have also referred in the PPT. So you can also go through that to understand these in more details. Okay, thank you.